Hi, everyone. Thanks for coming to my talk. Normally, before I give a talk in a conference, I like to thank the organizers broadly, but I am an organizer of this conference, so maybe what I'll say instead is thank you to the other organizers for all of their great effort in putting on this conference this year. And thank you to the session leaders, Fraser and Svenkar, for inviting me to talk in this session. I'm excited to see everyone else's talks and to chat with y'all. So this work is based on my thesis, which I defended in April of this year. I hope it's somewhat accessible. The goal was to be broadly accessible to people in math generally. So hopefully at least, grad students in topology, I'll find it, digestible. We'll see. And if not, you can come to my office hours. Okay, so the title of this work is Homology, Cobordism, and Smooth Knot Concordance. It is a dissertation, but also just a talk presented by me. And my advisor was Jen Hom. It's sad to say was, but she was my advisor. Okay, so we'll start with some background. Let our knots K be smooth embeddings of S1 and S3. And we'll note that the set composed of equivalence classes of knots with binary operation connects some forms of monoid. It fails to be a group because there are no inverses. We have this sort of obvious identity element, which is sort of like a circle as we refer to it colloquially, but we don't have inverses. And so if we might want to induce group structure on this object, a way we would do that is through the following equivalence relationship. So if we let K naught and K1 be two oriented knots in the 3 sphere, we say that they are cat concordant, meaning concordant in some category, if there exists a proper cat embedding of an annulus, S1 cross the interval that's sitting in S3 cross the interval in such a way that the annulus is co-bounded by the two knots on the ends. This forms a group. Now we have inverses, where I think I'll define that actually on a slide in a little bit. So I won't say what the inverses are just yet. I'll just kind of claim that they exist. And the schematic that you want to keep in mind if you've never thought about concordance, and if you haven't, you should hop over to the concordance topic group and learn a little more there. But this is a schematic of a concordance, down a few dimensions, but we're looking in this for manifold S3 cross the interval, and we're seeing these sort of maybe crazy knots on the ends, and the concordance just means that they co-bound this annulus in the center across the interval. Okay. Now we'll define specific categories of concordance. The most relevant one for this talk is smooth concordance, where this annulus is smoothly embedded. And then the group that we define is the smooth concordance group. Okay, maybe I'll tell you a little bit more about the smooth concordance group. Smooth concordance inverses of knots are defined to be, you take the knot, you take the mirror image of the knot, and then you reverse the string orientation. And that gives you the concordance inverse. And then the point is, if you imagine that the orientation of my hand is reversed, if you take the connect sum, that will always give you a smoothly sliced knot. And sliceness is now our identity element. So it's knots that are concordant to the M knot. And I've just written that out for you in symbols here. Some things that are known about this group and its structure is that there is, so there are slice knots. Slice knots do exist. So that is sort of trivial torsion elements. There are infinite order elements, and we know that there are 2 torsion elements. So for example, the figure 8 knot, which is denoted in, I think that's Alexander-Briggs notation for sub 1, satisfies that it is concordant to its concordance inverse. So this would tell you that in particular, the knot is at most order 2, and then you can sort of, here's a picture showing that to be the case. You can show that it is in fact exactly order 2 by obstructing sliceness. And so for example, one way to do that with this knot is to show that its determinant is not a square integer. So in fact, it is not slice, but it is concordant to its concordance inverse, and so it must be order 2. One other category of concordance I want to define, because I'm going to reference it later, is rational concordance. One thing that I forgot to mention that I'll mention now is another way to think about smoothly sliced knots is those knots which bound a disc in the four-ball. And you can see this by you cap off that concordance with the unknot. And so in rational concordance, we can define, you can read this definition if you like, but what we really care about is the identity in this group. And rationally sliced knots are those knots which bound a disk in some rational homology four-ball. And so rational homology four-ball is some four-manifold that has the same rational homology groups, so homology groups with coefficients, the rationals, as the four-ball. So for example, the four-ball is a rational homology four-ball, but it is a broader category perhaps. So I've just defined that group for you. Great. I defined my identity element for you. The identity element in the smooth concordance group is smoothly sliced knots, knots about a disk. This is nice. I gave you an example of a smoothly sliced knot. So this is, I believe 6 sub 1 is the stevedore knot, but don't quote me on that. But this is actually 6 sub 1, and it is actually smoothly sliced. This schematic does not, of course, give you the actual smooth concordance, but it does exist, and you can find it topologically smoothly. Great. Again, I've already told you this, rationally sliced knots that bound a disk in the rational homology four-ball. A thing to note is that rational sliceness is coarser, finer. I always forget which adjective to use there, but in particular, smoothly sliced knots are a proper subgroup of rationally sliced knots. As we've noted, the four-ball is a rational homology four-ball, so this should make sense to y'all. But we note that it is a proper subgroup. There are rationally sliced knots that are not smoothly sliced. And that is sort of an interesting subset to consider and to try to prove that such knots are rationally sliced and fail to be smoothly sliced. It's not always easy to do, and we'll explain why that is the case over the rest of this talk. One such example is the figure 8 knot 4 sub 1. It is rationally sliced. And this is one of the attributions I've seen given is to Cochrane based on earlier work of the Ronalds, Van Tuchel, and Stern. But I've also seen other attributions. So just want to make sure I mention that. But he also showed that this knot is rationally sliced. And it is known to be not smoothly sliced because, for example, like I told you, you can use the determinant to obstruct it. Great. This is just a picture. And this is just saying that the figure 8 knot is in some rational homology cobordism, it is concordant to the unknot. Okay. Now I'm going to define cobordisms. So again, our knot is a smooth embedding of S1 and S3, and we perform zero-framed Dane surgery on K. This I'm going to describe Dane surgery here in symbols for anyone who's unfamiliar. You're just carving out a tubular neighborhood. You're gluing in S1 cross D2 in such a way that that the meridian goes to the meridian of S1 cross D2 goes to the Seifert longitude, which is the longitude that has linking number with the knot 0. This gives your framing of your Dane surgery, and of course you can define any other integer framing. But we care in particular about zero surgeries, and we refer to this through manifold that you get after performing this operation as the zero surgery of the knot. And now I'm going to describe in pictures. I'm particularly proud of this sequence of pictures. I hope you like it. So here's some knot. We carve out a tubular neighborhood. Now it's in S3. That's the sort of like amorphous pink. And we take a solid torus and we glue it in. And we do it in such a way that that meridian, that little blue curve on the solid torus, is going to the Seifert longitude. I'm not sure of the writhe of this knot, so perhaps the longitude, the actual Seifert longitude might have some twists in it, but this is just a schematic. Great. Okay. Now, I don't want to consider my manifolds up to isomorphism, my zero surgeries. I want to consider them up to homology cobordism. And so this is a sort of general definition of homology cobordism. My homology is integer homology. So given 2, 3 manifolds, y1 and y2, we say that they are integer homology cobordant. If there exists a 4 manifold that is co-bounded by these 2, 3 manifolds in such a way that the inclusion maps of the boundaries into the 4 manifold induce isomorphisms on the relevant homology groups. Now, if we started off with our 3 manifolds as zero surgeries of knots, we can define a slightly stricter, slightly more specific cobordism, where we say that these manifolds are integer homology cobordant relative to meridians if the positively oriented knot meridians of, in this case, K1 and K2 are homologous. So in particular, they are representatives of the same class in H1 of that cobordism of W. And the way that you can think about this is it's sort of like fixing or knot orientations, because a priori, if I just, gave you some homology cobordism between 2 zero surgeries, it could be the case that, like, for example, the negatively oriented knot meridian of K1 was homologous with the positively oriented knot meridian of K2. And so we just sort of want to think about that as like fixing these orientations in such a way that the positively oriented knot meridians are homologous, the negatively oriented knot meridians are homologous. And we'll explain why that's relevant in a minute. It's just sort of a technical condition. So if this doesn't make sense, don't really worry about that. But here is the picture that we have in mind. So now the cobordism is not, when we looked at concordance, we were looking for this sort of annulus across. This is just saying that the entire cobordism exists and it's co-bounded by these 2, 3 manifolds. And there's sort of something special happening on the level of homology. I've just written stars. You can't draw a picture there, but that's just saying something sort of special is happening on the level of homology. Great. Okay. Motivation for this work, the why. And before you ask, yes, I did handwrite all of these fonts, and it was absolutely a good use of my time. Okay, so say we start off with this relationship between our 2 zero surgeries. We have some knot K1, we have some knot K2, and there is a integer homology cobordism relative to meridians between them. You might ask, does this imply that the knots need to be smoothly concordant? And when I was giving this talk for my thesis, there was a lot of non-math people in the audience, family and friends. And so I told them to think about it like, the soup can imply soup can. Stay tuned to find out. And the reason why this might be an interesting question to ask is that the reverse implication is true. And here's just a quick sort of proof of that. The statement is just saying that in general, the question of whether 2 knots are concordant in some category is closely related to the question of whether their zero surgeries are homology cobordant in that category. And the reason for that is because, like I said, this reverse implication is true. And you can see that I've just written out how to understand that here. So if you have some, you can basically take what you're going to do. I'll sort of describe it in words here. And if you want to pause and read the technical procedure here, you can. But the idea is that you do zero surgery along the concordance annulus between your knots, and that will give you a cobordism that is now relative to meridians is an integer homology cobordism. Oh, and I actually wrote that there. Yeah, so they're not too hard to understand, maybe worth kind of working through in your mind. Right, so the reverse implication is true, and we might wonder if the other direction is as well. And here's a little bit more history of the question to further motivate it. The what was known. So originally there was a conjecture by Kirby and Ockblut in the Kirby problem list. It's, I believe, 1.19 and subsequent remarks that says the conjecture was originally stated that if 2 knots have the same zero surgeries, then the knots are smoothly concordant. And same meaning, like homeomorphic, these are the same 3 manifolds. Kirby and Melvin in 1978 showed that this is true whenever one of your knots is the unknot. So in particular, the unknot only shares zero surgeries with knots that are smoothly sliced. Okay. The next work in 1983, Livingston gave a counterexample to this conjecture as stated by providing a family of knots that are not smoothly concordant to their reverse. So that's reverse is just reverse the string orientation. So it's sort of an interesting class of knots. It's worth looking at this paper if you can find it. A little hard to find online. But the point here being that zero surgery does not see the string orientation of a knot. It does not take that into consideration anywhere. And so, of course, a knot and its reverse always have homeomorphic zero surgeries. But this class of knots is not, does not satisfy the concordance. And so that's why we might look at a revised version of the conjecture where we further state that the knots have the knots with relevant orientations are smoothly concordant. And this will also tie into why we considered homology cobordism relative to meridian, because this just sort of helps us bypass counterexamples like the one that Livingston showed. So we can sort of get more at the meat of this revised conjecture. Some further history. So after all of that, in 2011, Cochrane, Franklin, Hedden, and Horn gave a family of counterexamples from two knots having homology cobordism relative to meridian, zero surgeries, and being smoothly concordant. And then in 2015, Yasui disproved the AK conjecture in the revised form. So then you're asking, okay, what remains open and why should we care? Why should we care? Right. So I'll just note here that these two counterexamples, these two families of counterexamples were all infinite order knots. And I believe so we used gauge theory. Cochrane, Franklin, Hedden, and Horn, I believe, used Thurston-Benniken numbers to obstruct smooth concordance. But basically, the point is that both of these proof techniques require that your knots be infinite order. And why might that be relevant? And why might that be maybe missing some other part of the question? Why? Okay. So like I just said, it's known that there exist knots where they're infinite order, or they represent infinite order classes in the smooth concordance group. The most interesting version of this question asks, does there exist knots where one of them is smoothly sliced and it shares a zero surgery with a knot that is not smoothly sliced? The reason this is most interesting is if such a pair of knots existed, there's a well-known technique using knot traces that would allow you to build an exotic S4. So this would have profound implications for the remaining open parts of the smooth 4D Poincare conjecture. And I like to hear make a joke that if I had proved this, well, I wouldn't be getting just a PhD, I'd be getting a Fields Medal. But I didn't prove this. Instead, this is what our question is. Do there exist knots of non-trivial torsion such that their zero surgeries are homology concordant relative to meridian? And these knots are smoothly concordant. So we're asking for non-trivial torsion. We're sort of saying, okay, we know we have counterexamples in the infinite order case. We'd love to know something about smooth sliceness. It's this sort of trivial torsion. Let's approximate trivial torsion. Let's get a little closer to it with non-trivial torsion. So in particular, the only non-trivial torsion known to exist in the smooth concordance group is order 2 elements. So that's the question we're going to answer. And then we say, okay, let's sort of try to set up an example of two knots that we hope could possibly be smoothly concordant. And so the pair of knots that we're going to look at, we required that they be rationally concordant. And in fact, both of them are rationally sliced. Does this further requirement mean then that we have smoothly concordant knots? So the results, what I did, again, that's their question, just rewrote it. And our answer is no, and still no. So I will give you now a pair of knots that one of them is non-trivial torsion, one of them is order 2, or representative of class, whatever. The knots are both rationally sliced, and their zero surgeries are homology cobordant relative to meridian, but the other knot in the pair is infinite order. So in particular, they are certainly not concordant. And here is my theorem just written in technical language. And here's the proposition, which clarifies which two knots I'm going to use. And I'll now explain them to you. Side quest. Oh, no. Oh, satellite operators. So I just need to quickly review satellite operators before we dive in. So given a pattern, which is some knot in a solid torus, we'll denote this such knot as P, and it's an S1 cross C2. We're going to be mapping this into a tubular neighborhood of some knot K. This pink pattern I've drawn is called the Major pattern. It has, it's sort of famous in four-dimensional topology for construction of exotic four manifolds. And it's a relatively simple pattern. It has winding number 1. It's relatively uncomplicated. And this is a tubular neighborhood of the figure 8 knot. So we define a satellite operation as mapping S1 cross a point where the point is in the boundary of D2, and we're sending it to the Seifert longitude of our knot. And then the image of the pattern under this mapping gives us the satellite knot, which we write P of K, where P is our pattern and K is sometimes called the companion. And now I've actually drawn for you here what this satellite knot is. Maybe I'll just note that the mapping sends, we'll just one copy here. So then it goes here. And that's hopefully easy to see from what the satellite knot looks like. This is a nice satellite knot to draw. The writhe is 0 of our companion, so there's no additional twisting required. You can actually just see the satellite knot, and that will be one of the knots that we're considering. Oh, why are we using satellite knot operation, and why is it interesting? Satellite operators, which is an operation defined on isotopy classes of knots, they descend to well-defined self-maps on the smooth concordance group. In general, they're not homomorphisms. In fact, Matt Hedden has a conjecture that the only time they are homomorphisms is in sort of non-interesting cases. So in particular, the identity satellite, the satellite operation that reverses string orientation, and the zero map that just sends everything to 0. That those are, he conjectures those are the only homomorphisms that come from satellite operations. So then the question might be, to what extent does a satellite operator or the map induced fail to be a homomorphism? So for example, does it send torsion elements to torsion elements? So that's sort of the side question. Is this not torsion? Because as I've told you, 4-1 is torsion. So does the Major pattern send this torsion element to a torsion element? So those are going to be our two knots. The figure 8 knot, I've given some justification for why I chose it here. And then the pattern, we're going to take the Major pattern and we're going to operate on this knot. And so we're going to take the figure 8 knot and a satellite of the figure 8 knot. And the reason I chose this pattern, there's sort of a few reasons. It's an unknotted pattern and it has winding number 1, where by unknotted, what I mean is if you take the unknot and you operate on it with this pattern, then the resultant satellite knot is unknotted in S3. And that's maybe worth kind of just thinking about for a second and, you know, maybe go back and see what the Major pattern looks like and say, oh, of course. And why it being unknotted is interesting for us is that if some knot is sliced in some category and our pattern is unknotted, then the satellite knot will also be sliced in that category. I don't know if I include, oh, I did include a picture. This graphic is also really nice. So here's 4-1. It is rationally concordant to the unknot. So it is rationally sliced. And then if we operate on both sides of the concordance with our satellite, or, you know, if you satellite sort of along the concordance annulus, you'll see that on the left-hand side now we have that satellite knot and it's still concordancy on knot. And then another implication of of the fact that it is unknotted and has winding number 1 comes to us from Cochrane, Franklin, Hedden, and Horn, who tell us that for any such pattern and for any knot, we have this integer homology cobordism relative to meridian between our zero surgery. So that just comes for free. So this is just summarizing that we have everything that I claimed my 2 knots in the counterexample satisfy. These 2 knots do satisfy. So the question is now, are they smoothly concordant or not? And is this not even torsion? If they're not smoothly concordant, is this not even torsion? So how we're going to show this, I'm going to give a very high level description of Heegaard Floer theory. Hopefully you've already seen like an introductory video of it. Right, knot Floer homology takes as input some knot K and S3. It's more broadly defined, but for our cases, we'll just stick to S3. This theory was introduced by Oshvath-Szabo and independently by Jake Rasmussen. And what we get out is C of K over R of K, which is a bigraded chain complex, and it's both freely and finitely generated over the ring. I'm going to use the ring F2 adjoin UV, so the polynomial ring with 2 variables over the field of 2 elements. Why I might want to use Heegaard Floer theory when asking questions about concordance is it admits several concordance invariants. Here are some examples. There is the tau invariant due to Oshvath and Szabo, which takes on integer values. And the epsilon invariant due to Hom and takes on the values -1, 0, and 1. But the problem for us in this case is that these are actually rational concordance invariants. So in particular, they vanish for our knot. So everything's just 0. And so of course, when an invariant is 0, it does not tell us anything interesting. Right. A concordance invariant being non-zero would tell us that this knot would not be slice in that category. But these invariants vanishing is sort of, we're out of luck for using this technique. So what we're going to do instead is use involutive knot Floer homology, which is due to Hendricks and Manilescu. It again takes as input K and S3. It is again more broadly defined, but we're going to restrict to knots in S3. And it gives us output our knot Floer complex with this additional data of iota K, which is a self map on the chain complex. It's not quite an involution on the nose, but it's close enough. Okay, so we have the knot Floer complex of the figure 8 knot. It is well understood and it has been well studied. We would like the knot Floer complex of our satellite. It would be so wonderful if we understood how knot Floer complexes behave under satelliting. But unfortunately, as most knot theorists know and are deeply upset by, this is not the case. We don't understand how these behave under satelliting. So we're going to use one more refinement of Heegaard Floer theory. We're going to use bordered Floer homology, which is due to Lipschitz, Oshvath, and Thurston. Takes as input 3 manifolds with boundary. So perhaps knot complements in S3 or link complements. Both of these have toroidal boundary components, one or several. And it gives us output differential graded modules over a differential graded algebra. In the case where we're looking at knot and link complements, all of our boundaries are toroidal. Our algebra is the torus algebra. It is just a graded algebra. And we'll note that what these invariants look like. When there's one boundary component, we get 2. It's one equivalent invariant. So we just call it like the bordered invariant. But it comes in 2 forms, but they're dual in some sense. So they actually contain precisely the same data. So there's the type A structure and the type D structure. And basically, we might choose to use one or the other for reasons that will become clear in a moment. I just wanted to write them out that if there's 2 boundary components, you choose for each boundary component if you want to view it as a type A or type D structure. And the reason this theory is so wonderful and why this duality is interesting is that it allows us to perform a pairing operation. So what we do topologically is glue 2 manifolds along their boundary components. And what we do on the algebraic level is a tensor product. So it's an A infinity tensor product, but in our case, it's equivalent to just taking a box tensor product because our modules are bounded in some proper sense. And so the tensor product operation that I'm going to use is I'm going to take the type A structure of the complement of the figure 8. I'm going to take the box tensor product with the type DD bimodule of the measure pattern in the solid torus, where my two boundary components come from, one is the neighborhood of the pattern inside the solid torus, and the other comes from the solid torus itself. And what I will get is the bordered invariant that corresponds to the complement of the satellite knot. Oh, yeah, and I always want to give credit to Adam Levine for computing this bimodule. These are very difficult to compute, but the reason I even started on this project was that I had this bimodule computed so I could do the computations relatively easy, comparatively. Okay, so the point of all this is I'm going to compute the bordered invariance of my satellite knot to then compute the knot Floer complex of my satellite knot. There's a well-defined algorithm for converting the knot Floer complex of a knot to the bordered Floer invariant of the knot complement. And we claim that we can sort of reverse engineer to go in the opposite direction. And then once I have the knot Floer complex, I will compute its involutive knot Floer complex. And then I will use that data to obstruct it from being torsion in the smooth concordance group. And the fact that I will use here is due to Hom, Kang, Park, and Stoffregen, based on earlier work of Zemke that says we can use almost local equivalence class of our almost iota K complex of a knot to obstructive torsion. Sort of just a technical condition if you're interested in this. Again, please come to office hours and I'd love to give you a little bit more info. Okay, this is just describing it in pictures. Take our knot, take the satellite of the knot, compute the bordered invariant, and then take the bordered invariant and do some work using we'll decategorify the Alexander polynomial and use what we know about how genus and some other invariants behave under satelliting to build the knot Floer complex. This is just clarifying where everything's coming from. Maybe pause on the screen, look if you'd like. Right, this is just reiterating what's going on. If two knots are smoothly concordant, then there has to be some equivalence relationship between their iota K complexes. And so we'll show that for any finite n, we can obstruct this, this type of equivalence between the iota K complex of the unknot and any finite linear combination, which in this case is tensor products of our knot Floer complex, which will obstruct it from being torsion. And so in particular, will tell us that it must be infinite order. And that will imply our lemma, which will in turn imply our theorem. Oh, and then I'm done. And that's my sweet dog, Winnie. Great, thanks for coming to my talk. Sorry for running a little bit over. See you at office hours.